A telescope the size of a tennis court floating 1.5 million kilometers from Earth just looked at a patch of the night sky roughly equal to 3 full moons held up against the darkness, stared into it for a total of 255 hours across multiple observation sessions, and returned data that contained the positions, shapes, distances, and physical properties of nearly 800,000 galaxies. Not 800,000 stars. 800,000 entire galaxies. Each one containing hundreds of billions of stars of their own. And that was in a region of sky so small that you could cover it completely with your outstretched hand. That result, published in June 2025 by the International Cosmos Web Collaboration and later expanded into an even more detailed map of cosmic structure, did not simply add numbers to a catalog. It forced astronomers to rethink how much structure exists in the distant universe and how quickly galaxies were able to form in the early cosmos. The James Webb Space Telescope did not make the universe bigger. It revealed parts of the universe that earlier instruments simply could not observe clearly. To understand why the 800,000 galaxy number is so remarkable, you have to understand what was previously known about the same region of space. The famous Hubble Ultra-Deep Field Image, released by NASA in 2004 and celebrated for years as one of the deepest views of the distant cosmos ever captured, revealed approximately 10,000 galaxies in a tiny patch of sky. That image was considered an extraordinary scientific achievement. It was studied for years and became one of the most recognizable scientific images ever produced. But it was also limited by the wavelengths Hubble could observe. When astronomers began observing comparable regions with Webb's infrared instruments, the picture became dramatically richer. The difference was not simply that Webb produced a larger image. It detected much more faint and distant structure that had been extremely difficult or impossible to see before. The reason those galaxies were hidden becomes clearer once you understand the physics. Light from ancient and distant galaxies does not arrive looking exactly the way it left its source. The universe has been expanding continuously since the Big Bang. As space expands, the wavelengths of traveling light are stretched along with it. This process shifts light toward longer wavelengths. Visible light, which human eyes can detect and optical telescopes are designed to capture, can be shifted farther into the infrared as it travels across the expanding universe. The farther away and older the source, the more significant this redshift can become. Hubble could observe some infrared wavelengths, but Webb was specifically designed to observe much deeper into the infrared. Its 18 gold-coated beryllium mirror segments span approximately 6.5 meters across, allowing it to collect far more light than Hubble. Combined with its infrared instruments and extremely cold operating environment, Webb can detect faint sources whose ancient light has been stretched dramatically during its journey to Earth. When those instruments were pointed toward regions that earlier observations had found relatively sparse, the darkness began to fill with distant galaxies. They had not suddenly appeared. They had been there all along. We simply lacked the technology to see them properly. This is what makes the result scientifically important. The universe was not necessarily misunderstood because previous observations were wrong. Rather, our picture was constrained by what our instruments were capable of detecting. Every deep field survey, galaxy catalog, and cosmological model was built using observations that covered only certain wavelengths and depths. Webb is allowing astronomers to investigate portions of cosmic history that were previously far more difficult to study. And the number of galaxies is only part of the story. Webb has also revealed something much more challenging. Some galaxies observed during the earliest periods of cosmic history appear surprisingly mature, bright, massive, or chemically evolved for their age. The standard cosmological framework, commonly called lambda-CDM, describes a universe that begins with extremely small fluctuations in matter and gradually builds larger structures through gravity. Gas collapses. Stars form. Small galaxies develop. Galaxies merge. Gas continues falling into galaxies. Over enormous periods of time, these processes produce the large spiral and elliptical galaxies we see today. The model makes predictions about how quickly galaxies should grow, how massive they should become, how bright they should be, and how chemically enriched they should be at different points in cosmic history. Webb has found several early galaxies that challenge some of those expectations. For example, astronomers have identified galaxies whose light comes from a time when the universe was only a few 100 million years old. Some are surprisingly luminous and show evidence of substantial star formation. That matters because heavy elements such as oxygen are not produced in the original Big Bang in the quantities we see in mature galaxies. They are produced through stellar processes and distributed into surrounding gas when stars evolve and die. So when astronomers detect substantial chemical enrichment in extremely young galaxies, it raises an important question. How quickly did the first generations of stars form? How quickly did those stars live, die, and enrich their surroundings? And how rapidly could the next generation of stars and galaxies develop? Webb's observations do not mean that the standard cosmological model has been destroyed. That distinction is extremely important. There is no scientific consensus that lambda CDM has been disproven. Instead, astronomers are examining whether certain assumptions about early star formation, galaxy growth, feedback, dust, stellar populations, and dark matter need to be adjusted to explain what Webb is seeing. Some researchers suggest that early star formation may have been much more efficient than previously assumed. Others are investigating whether our understanding of dark matter and the growth of early structures needs refinement. And some scientists are exploring whether entirely new physics could eventually be required. The data is still being studied. But one fact is already clear. The early universe is proving to be more complicated than the simplified picture we once had. And there is an even larger realization hiding behind all of this. The universe Webb is revealing is not the entire universe. It is only the portion from which light has had enough time to reach us. The observable universe is the region of space from which information can currently reach Earth. Light travels at approximately 300,000 kilometers per second, but because space itself has been expanding throughout the history of the universe, the distances involved are far more complicated than simply multiplying the speed of light by the age of the universe. The universe is approximately 13.8 billion years old, yet the observable universe has a radius of roughly 46 billion light-years. That sounds impossible at first.